Hello and welcome to the first ever explanation video from CB Astronomy. Again, my name is Chris. I'm your host for the next 6 or 7 minutes. I've chosen this topic very carefully because I wanted my first explanation video to be something that was meaningful to me, and the topic I've chosen is stellar evolution. The reason I've chosen this topic is because a few years back I had to do a presentation as a part of college, and the topic could be anything in science you happen to be interested in. So me being interested in astronomy, I happened to choose this. And I wasn't great at public speaking at the time. I'm still not fantastic at it, but people engaged really well and gave me a lot of positive feedback from it. So it gave me a confidence boost, and it's what sparked my interest to start talking about science. So we'll just crack straight into it. So a star is born from a region of space which it has really dense clouds of gas and dust. These regions are called nebulas, or nebulae. A nebula has all these dense clouds, so over time the gas and dust will clump and bind together. When it reaches a certain mass, it'll contract, and because of that contraction it will heat up. The reason it contracts is because of its own gravitational mass. It causes everything to pull to the center. So over time this keeps on going and going. This process is called accretion. So as more and more matter combines together and contracts and heats up, the gas will eventually start to glow. When this happens, the region is known as a protostar. Protostar will keep on heating and contracting and heating and contracting until it reaches a temperature of 15 million degrees. This is the temperature that fusion occurs at. Now, if you're not massively familiar with fusion, don't worry. I'll be doing a separate video on that, covering both its use in stars and its like it being the holy grail of clean energy. So so now that fusion is occurring in the core of the star, it creates an opposing force to its own gravitational contraction. So in essence, a star's life after ignition is a constant battle between its fusion trying to blow it apart and its mass trying to grab everything together. And for main sequence stars like our sun, this battle can go on for about 10 billion years. And before I get too ahead of myself, I will just briefly go through a bit of fusion. So hydrogen is the most common element in the universe, and it consists of just one proton and one electron. And with the increase in heat and pressure that's in the center of the core, it makes the atoms accelerate. Now normally the atoms would just pass each other or repel each other, but with the increase in heat and pressure, they don't have time to get out of each other's way, and it results in a collision. Now, when two hydrogen atoms combine like that, it releases a big amount of energy, and it literally fuses the two atoms together to form deuterium, and then onto helium. So for main sequence stars, as I said, it goes on and on for 10 billion years. This is just because of the size of the sun. It's at a great range where it just has a really long lifespan. But so once all the hydrogen has fused together, it will leave just a helium core there. Now when this happens, the core will contract, heat up, and some more reactions go on in the outer layer of the core. Now it takes a few more steps, which as I said I'll go into more detail on in the fusion video, but it will eventually go on to fuse into just a pure carbon core. Now when this happens, there's another contraction. The outer layers of the star will expand out and form a planetary nebula. When this happens, it'll expand out, it'll cool, and it will shine less brightly. And when all this is said and done, what remains is a white dwarf. A white dwarf is just a core of just pure carbon. It's really hot, it's really dense, and it just keeps on shining for millions and millions of years. But that too eventually will cool down, and when that happens, when it stops shining, it's cool, it is known as a black dwarf, and it is declared a dead star, which is very sad. But white dwarfs do go on sometimes to form other reactions in the universe, which I'll talk about in my next video. Excuse me. So that's the case for a nice smallish star, but there are a lot of stars in the universe that really like outdo the sun in terms of size. So just give you an example, there's a star called Betelgeuse. It is part of the Orion constellation, so if you're looking at it, it'll be in the top left corner, and it has a reddish tint to it. But Betelgeuse has a radius of 820,700,000 kilometers. Sorry, I'll say that again. 820,700,000 kilometers. That is absolutely massive, and compared to the sun, like the sun has a radius of 695,700 kilometers. Like, it's easily 20 times the size without having a calculator handy to do the maths. But Betelgeuse is approaching the end of its life cycle, so in the interest in avoiding spoilers, I will crack on. Excuse me. So in the initial, so the massive stars form in more or less the same process as the smaller main sequence stars, and so they'll form in a nebula, accretion will occur, protostar, all that will still happen, it'll still ignite. But one of the main differences that is noteworthy is the amount of time that the massive stars will burn through their hydrogen in. As I said, a star like our sun will burn through in about 10 billion years, which is absolutely fantastic. It gives a great long period of time for life to evolve on its planets, and that's brilliant, that's why we're here. But with the massive stars, that's not the case. The massive stars will burn through their hydrogen in a couple of million years, which, like, I've heard them being described as the rock stars of the universe. They live fast, die young. So once all of their hydrogen is fused into helium, it'll follow a lot of the same process. Fusion cycle will just keep happening. So go hydrogen, helium, on and on to carbon. So continue on forming new elements until iron is formed. Now, iron is a death sentence for massive stars because iron is an energy absorbing element. So once iron is formed in the core of the star, it's dead, gone. The core will contract in less than a second, and the massive No! Oh man, I'll tell you what, I gotta keep recording and just see what I can salvage. Oh man, that sucks. Alright, where was I? Oh god. Yeah, so iron's formed, the core contracts really quickly, less than a second. The core, which will be of decent width across, will contract in really quickly and result in a explosion called a supernova. I'm sorry. The phone fell off the table and just it's ruined. Right, we keep going anyway. So the core contracts and results in a supernova explosion, and this blasts the outer shells of the star into space. So that is not necessarily the end for the massive star though, because sometimes the core will survive and it can take a few different forms. Now I'm going to go into a lot of detail on this in my next video. I have it all written. All I have to do is sit down here and talk to you about it, and it'll be uploaded during the week. So I'm just going to keep this section brief. But there's a few different forms the massive stars will take. So if the core is between 1.5 to 3 solar masses, it will contract to form a neutron star. Neutron stars themselves have a few different variations, which are all really, really fascinating things. But when the core is larger than 3 solar masses, it will contract to form a black hole, which is one of the black holes are the most amazing, astounding, and just brilliant things in the universe. I can't stress how fascinating they are. I really enjoy them, and all the theories that have come about of, especially like in the early days of science and the predictions that were made and held true to this day. It's just fascinating stuff, and I do have a separate video for black holes, and I will briefly talk about them in my next video as well. But yeah, so black holes are class. I'm gonna end it there for today, because as I said, I have videos on the way. If you enjoyed the video, please give it a like, subscribe to the channel so you can get more content. As I said, there's a lot of stuff coming on black holes and the afterlife of stars, a lot of really interesting topics. I'm going to be doing a time dilation video as well, so if you've seen the movie Interstellar, you would have got an idea what that's about, but I will be going into a lot of detail on it because I think that as well is brilliant. But yeah, so please like and subscribe to the channel. The links to my Twitter and Instagram will be in the description. Please follow them as well so you don't miss out on any content. And yeah, thanks for watching, and thanks again to my buddy Sean for letting me use this lovely cabin as my studio. Yeah, see you later.